This is the third video in a series, where I cover everything you need to know to build a GPS receiver from scratch. In the previous video, I introduced the concepts of correlation, cross-correlation, and autocorrelation. In this video, we'll build on those concepts and discuss GPS signals. More specifically, we're going to talk about the signal we'll use in our GPS receiver, the CA signal, how binary information is encoded in that signal via modulation, and how we can distinguish signals from different satellites using a technique called CDMA. Let's start with the CA signal. In the first video in this series, I said that GPS satellites continually transmit radio signals. They actually transmit multiple signals on multiple frequencies, as summarised in this table from Wikipedia. There's a lot of information here, so let me step you through it. A band is a frequency on which a GPS satellite might transmit. Each band can be split into two phases, with different information on each phase. We'll cover that later. Some of these signals can be used by civilians, but some require encryption keys that are only available to the military. Modern GPS receivers likely use a combination of the civilian signals to increase their accuracy, but almost all of them would use what's called the coarse acquisition signal, or CA signal. It's called this to contrast it with the precision signal used by the military, coarse versus precision, and because it can be used to help acquire that more precise signal, acquisition. It's transmitted by all GPS satellites, which makes it widely available, and this is the signal we'll use in our receiver. Within the CA signal is something called the navigation message. It's a binary message that's transmitted at the blistering speed of 50 bits per second. It contains all of the information we need to calculate a satellite's location and the time of its onboard clock. I'll talk about how you do that in a later video. Let's use the term di of t to represent the navigation message bit of satellite number I at time t. You might be wondering, isn't the CA signal a radio wave? How is a binary message transmitted using an analog radio wave? Well, this is achieved through a process called modulation. Generally speaking, this is where you take a higher frequency signal, called the carrier signal, and you change it in some way to transmit a lower frequency signal, called the modulation signal. For example, you've probably heard of amplitude modulation, AM, where you change the amplitude of the carrier, and frequency modulation, FM, where you change its frequency. Both of these techniques are often used to broadcast music. The frequency range for music is around 20 Hz to 20 kHz, but the frequency range for FM radio stations is around 90 to 110 MHz, which is thousands of times greater than the frequency of music. This is an example of a lower frequency signal, the music, being modulated onto a higher frequency signal, the radio wave. In the case of the CA signal, the carrier is a radio wave at the L1 frequency. We'll use the term Fi of t to represent the amplitude of satellite number I's carrier wave at time t. The modulation signal is the navigation message, di of t, which is transmitted at 50 bits per second. So how is the navigation message modulated onto the carrier wave? Well, instead of amplitude or frequency modulation, phase modulation is used. This is where the phase of the carrier wave, its horizontal position, is changed to encode binary data. More specifically, a technique called binary phase shift keying, or BPSK, is used. To see how this works, let's look at an example. Imagine this is our carrier wave, and we want to modulate a binary signal. The first step to using BPSK is to decide your data rate. Let's go with 4 bits per second. We divide each second into equal periods of time that each represent 1 bit, like this. Within those periods, if we want to transmit a binary 0, we leave the carrier unchanged. So at the moment, this signal is transmitting 4 zeros. If we want to transmit a binary 1, we apply a 180-degree phase shift to the carrier in the corresponding period of time, like this. Now we're transmitting a 1, followed by 3 zeros. A receiver can detect these phase shifts to decode the 1s and 0s. Notice that a 180-degree phase shift is equivalent to flipping the signal vertically, or multiplying its amplitude by -1. You can see this if I change the second bit from a 0 to a 1. We can use this to express the binary navigation message in terms of how it affects the amplitude of the carrier wave. Here are some bits that we might want to transmit. Zeros don't change the amplitude of the carrier wave, so that's like multiplying it by 1. And 1s negate the amplitude of the carrier wave, so that's like multiplying it by -1. Let's denote this mapped sequence of numbers d hat I to distinguish it from the original bits. Using this, we can express the process of BPSK modulation as simple multiplication. d hat I of t changes the amplitude of the carrier wave, fi of t, in a way that's equivalent to 180-degree phase shifts. This mapping is called polar non-return to zero encoding, and it'll be useful in the next section. So that's the signal of one GPS satellite, but, as I mentioned in the overview video, we need multiple to calculate our location. But aren't they all transmitting on the same frequency, the L1 frequency? Isn't that like multiple radio stations broadcasting on top of each other? How could you ever separate the signals? Well, if each satellite simply modulated its navigation message onto the carrier wave directly, as shown here, we wouldn't be able to separate them. To solve this, GPS uses a technique called code division multiple access, or CDMA, which is the topic of the next section. As part of CDMA, each satellite is assigned a unique code called a pseudo-random noise code, or PRN code. Like the navigation message, this is a binary code, and in the case of the CA signal, it's 1023 bits long. Here's a graph of the first 255 bits of Satellite 1's PRN code to give you an idea of what it looks like. So how are these codes used? Well, instead of modulating the navigation message onto the carrier wave directly, as we did in the previous section, a GPS satellite first computes the exclusive OR of its navigation message and its PRN code, then modulates that. I've introduced the term PRN I of t to represent the bit of satellite number i's PRN code at time t. The PRN code is transmitted at 1.023 megabits per second, which means the full code repeats once per millisecond, or 20 times for every navigation message bit. We'll talk about why all of this is useful in a second, but before we do, let's simplify our notation a little. Remember how we mapped bits of the navigation message based on how they affected the amplitude of the carrier wave? 0 mapped to 1, and 1 mapped to -1. It turns out that after applying this mapping to 2 bits, the exclusive OR operation is equivalent to multiplication. I've put some truth tables on the screen if you want to pause and check for yourself. That means if we also apply this mapping to the PRN code, we can write both the exclusive OR operation and the BPSK modulation as multiplication, and the signal transmitted by a satellite can be written as d hat I of t times PRN hat I of t times fi of t. Notice that we've placed a hat over the PRN term to indicate that the mapping has been applied. So how does all of this help us distinguish signals from different satellites? Well, PRN codes have some interesting properties, and they're all to do with correlation. Firstly, a PRN code has a strong positive correlation with an aligned version of itself. But as we discussed in the previous video, that's true for any signal, so it's not too interesting. However, it has a near zero correlation with misaligned versions of itself. In other words, its autocorrelation function has a spike at 0 as usual, but it's near 0 everywhere else, as you can see in this graph. The spike's a little hard to see, but it's there. Secondly, the correlation of any two different PRN codes is always near 0, regardless of their offset. In other words, the cross-correlation of any two different PRN codes is always near 0, as you can see in this graph, which has the same scale as the previous one, and this time there's no spike. Next, let's consider the signal we'd receive if multiple satellites were in range, and how we can use these properties of PRN codes to decode the navigation message bit of a single satellite. I'm going to step through a proof showing how this works. It gets a little technical, but I think it's really cool and helpful in building an understanding of how CDMA works. If you're not interested in the proof, feel free to skip to the next section, where I'll recap the important bits. From the previous section, we know that this expression describes the signal transmitted by a single satellite. It's the navigation message, exclusive ORed with the PRN code, which is then BPSK modulated onto the carrier wave. We can express both of those operations as multiplication because of the bit mapping we performed. Now, let's say we're receiving signals from satellites 1 and 2. Radio waves obey the superposition principle, which is a fancy way of saying they combine through simple addition. That means the signal we receive will be the sum of two of these expressions, one for satellite 1 and another for satellite 2. There'll also be some noise in the signals, which we'll denote N1 of t. It turns out that a receiver can record this signal in such a way that the carrier waves, the f of t terms, are replaced with constants. I'll explain how this works in the next video, but for now you'll just need to trust me. If we do that, we're left with this expression, where C1 and C2 are real valued constants, and N2 of t is different noise from before, but still just noise. So what happens if we record this signal for a short period of time, capital T, and calculate its correlation with a copy of satellite 1's PRN code over that period? Well, we get this integral. Our copy of the PRN code might not be perfectly aligned with the PRN code within the signal, so we'll offset it by some shift in time, tau. If we distribute the PRN code term and split the sum into 3 integrals, we get the following. The C1 and C2 terms are constant, so we can pull them out the front. Remember I said earlier that the navigation message is transmitted quite slowly, at 50 bits per second, or 20 milliseconds per bit? Well, if capital T is small, on the order of a couple of milliseconds, then the navigation message bits are likely to be constant over this period, and we can pull those terms out the front too. So we're left with 3 integrals. The second is the easiest to deal with. It's the correlation of satellite 2's PRN code with satellite 1's. We know from the properties of PRN codes that this is always near 0, so that term drops out, and we're left with 2. The first is the correlation of satellite 1's PRN code with a potentially misaligned version of itself. Again, from the properties of PRN codes, we know that if they're misaligned, that integral will be near 0, the term will drop out, and we'd just be left with noise. We don't want that to happen, so we need to make sure that our copy of the PRN code is aligned with the satellites. In other words, tau needs to be 0, and it can be removed. Now the first integral evaluates to a positive constant. We'll merge it with C1 into a new constant called alpha. The second integral is the correlation of noise with our copy of the PRN code, which also evaluates to a constant that we'll call beta. Alright, how do we extract the navigation message bit from this? Well, the signal might be much weaker than the noise, in which case beta will dominate and the result might not be correct. So this is the really cool part. When we spoke about correlations in the previous video, you might remember that I said for periodic signals, like the PRN code, you can calculate their correlation over multiple periods and the correlation will scale proportionally. What that means here is if we increase capital T, that is we record for a longer period of time, the signal strength will increase linearly. The noise, on the other hand, interferes with itself. Sometimes it's positive, sometimes it's negative, and it cancels itself out, such that its strength grows at a slower rate than the signal's. This means that we can improve the signal-to-noise ratio by recording for a longer period of time. Both alpha and beta will increase in magnitude, but alpha will grow faster than beta. In practice, recording for 1 millisecond gives a good enough signal-to-noise ratio for us to successfully decode a satellite's navigation message bit. That was a lot, but we did it. Let's recap the important points from this video. Our receiver will use the CA signal on the L1 frequency. The CA signal contains the navigation message, which in turn contains the information we need to calculate a satellite's location and the time of its onboard clock. Each satellite is assigned a PRN code. That code is exclusive ORed with the satellite's navigation message, and it repeats once per millisecond. And finally, we can decode the navigation message bit of satellite number I by recording the received signal for 1 millisecond, then calculating its correlation with an aligned copy of satellite number I's PRN code. The next video will cover the first stage of the GPS receiver implementation, sampling. We'll cover the hardware you need, how to configure that hardware, and the data it'll produce.